Hello, everybody. We didn't get a chance to do this in class, so I want to throw this out today and give you a quick tour of the steam tables. Now, the steam tables, as you're going to see them right here, are they're pulled out of a different textbook, and you have access to this version of them in Moodle up at the top where it says somebody else's steam tables. The reason I'm showing you these is, well, you can see the ones in your own textbook just fine. This one prints out better. So you're going to see this one again because I'm going to print it out and hand it to you. So that's why I'm going to show it to you here. You can also access the steam tables in HYSYS. You can access them. There's an Excel plugin. If you're feeling really clever and can figure that out, you can access it in Excel in some cases. There's various online ones. You can get it in an app on your phone. All of those have their own quirks and foibles, so I'm going to show it to you this way, and anything you learn in here is applicable on the electronic ones. It's just the electronic ones do some of the work for you. So, steam tables are typically broken into 3 sections, one that's talking about saturated, one that's talking about superheated, and one that's talking about liquid, just straight up compressed liquid. So first we're going to talk about saturated steam. Now, for reasons that we will talk about more in class very soon, Gibbs phased rule, that's the hint, when you have a single component, that's water, and it's saturated, that means it's right at its boiling point. That means you have 2 phases, 1 component, that means there's only 1 degree of freedom. And what that means is, at any given temperature, you can only have saturated steam at a particular pressure. And that fixes every single state variable. So if we look at this table that I have reproduced here, so again, you can download a copy of this and print it out, you can see that what we've got, and I'm getting a pen for us here, is like if you look here, there's 1 temperature, say 75 degrees Celsius, and if you want water to boil at 75 degrees Celsius, it only happens at 1 single pressure, and then every other piece on this table is fixed. So it's got where it says VL, that's the volume of the liquid, and that's a property. Do you notice it's volume per kilogram? So it's not like volume of this teacup, it's like volume, it's like the inverse of density. And then you also have volume of the vapor. You have the internal energy associated with either the liquid or the vapor under these conditions. You have the enthalpy associated with the vapor or the liquid in these conditions. And you have the entropy associated with the vapor and the liquid in these conditions. So that's all of this stuff over here. Now, you'll notice there's also some places where it has a delta. See that delta? What those deltas are is the change in enthalpy for when you go from the liquid phase to the vapor phase. So if you're doing some math and you need to know the enthalpy of 100% steam at a particular temperature and you know it's saturated, you just use this number, HV. The delta is the amount that you would add to get from the liquid number to the vapor number. So that's what's happening there. Okay, next slide. All right, hello, it's me again. I told you that steam tables tend to have 3 different tables in them, and yet I'm about to show you 4. Well, what's the deal here is that saturation can be arranged in order of temperature, and we also happen to have it arranged in order of pressure, just because it's convenient, because, right, it's not as though most of the time you say, hey, I'm in an environment where the temperature is, I don't know, 50 Celsius. What pressure does water boil at? That's not the world we live in. The world we live in is we say, oh, we are, whoops, I need to get a pen here, la, la, la. We are at about 1 atmosphere, so that's 1 bar is what I just circled there. And what temperature does water boil at, right? Like we tend to live at a constant pressure and then be looking for the temperatures that match that. Or maybe I just bought a instant pot, and so I'm at 0.2, I'm at 2 bar, I'm at 2 atmospheres, and I want to know what temperature that runs at. It runs at 120. So this whole table is the same thing as the previous table. It's just arranged in convenient values for pressure as opposed to convenient values for temperature. Piece of cake. Okay, I'm back again. This time we're looking at the next different table. It's called superheated steam. So just imagine in your head, I've got some water and I'm heating it up and I'm boiling it, and now it's all steam, so it's no longer saturated. There isn't liquid for it to be in equilibrium with, and I can just take that steam and continue to heat it. That's superheated steam. Now, we have one phase and one component. That means we have 2 degrees of freedom. So you can see the superheated table is a little funkier to read because you have to know what pressure you're looking at. So this is about half an atmosphere, half a bar here. And then you can also pick a temperature, right? Because steam exists that is superheated at all of those different temperatures and that pressure. And again, as we had before, we can have entropy, we have enthalpy, we have internal energy, and we have the volume per unit mass. What's new and different here is you're like, wait, where'd the deltas go? Well, there is no delta because there's no liquid for it to be in equilibrium with. And there's no, for example, enthalpy of the liquid because it's superheated steam. And one important thing I'm going to tell you right here, right now, is you might be thinking to yourself, oh my gosh. So if I know something's saturated, I'm going to look on the saturated table, or if I use my phone, I'm going to use the saturated part of the app. If I know I'm superheated, I'll look over here. I'll look at this kind of stuff. How do I know which one I am? And the great secret, which is really cool, is for any given set of conditions, matched temperature and pressure, it only, the state variables are unique to that condition. So for example, if you know that your temperature is 400 and you were to know that let me try and keep this on the same line. Boy, my eyesight is not as good as it used to be. And you knew that the enthalpy that went with that was 3,275.5. You would not be able to find that pairing anyplace else except at 0.3 megapascals, which is kind of where that is. If you went to look for that on the saturated table, you could find 400 degrees, but 400 degrees wouldn't go with 0.3 megapascals, and it wouldn't, as either just 100% steam or 100% liquid, go with 3,000, et cetera, et cetera. So every point on here in all of these tables is unique, and that's pretty cool. You'll want to watch the other videos that tell you about both interpolation and quality, because the quality does some interesting things to our math, but that's cool. So let me show you the last table we got. Okay, here is the final part of the steam tables. So for example, you see I've got the dregs of my tea here, and you will notice it is a liquid, right? Now, it's not a saturated liquid, right? It is not at the point of boiling under atmospheric pressure. It's not at 100 degrees C. It's at room temperature, and my office is really pretty cold, so it's probably at, maybe it's at 20 Celsius. And so what if we needed to do some math on this substance right here, right now? And well, it's not on the saturated table because, again, it's not on the point of boiling. It's not superheated. It is clearly not steam. What's the only thing left? The thing left is called compressed liquid. Now, few things about this table. For water, when it is a liquid, its properties are not strongly related to pressure. They're more strongly related to temperature. And you can see this because if you kind of look across here, 5 megapascals is about 50 atmospheres, right? This is the big number. And if you look at, say, what is a good place to pick? If we look at, let's pick 100 degrees here. And if we look at 100 degrees and we say, oh, look, its internal energy is 417, its enthalpy is 422, and then I go over here and I look at 10 megapascals, so we've just really ramped up that pressure, and you can see that my internal energy and my enthalpy increased by like what? Well, internal energy went down by 1 kilojoule per kilogram, and enthalpy went up by like 4-ish kilojoules per kilogram. And in the scheme of things, those are not big numbers. So, quite a lot of the time when we are working with what we call compressed liquid, you are fine, unless the pressure is very high, using the volume number, the internal energy, the enthalpy, or the entropy value from the saturated table just for the liquid part. You can get away with that. And then if you are at a particularly elevated pressure, you can do crazy interpolation to get into the middle of all of this stuff down here. Or, you know what? Heck, you pick the one that's close and you make an estimate. Sorry. When you get to the point, that is for what we call a first pass design. That's fine for what we will be doing with compressed liquid in this class. Compressed liquid is a thing that comes up in pumps. If you are about to spend $5 million of your company's money on a series of pumps, then you should, get the decimal places a bit more correct. But if you are just doing an estimate to understand about the energy requirements you expect, using, say, the enthalpy values here, you can call 3 megapascals, that's going to be like 5 megapascals, and you can kind of use the numbers that way. Much more important in the steam tables, superheated and saturated. Those are where we're going to spend most of our time. Okay.